Hi, I'm Travis Cuvelier, and I'm a PhD student at UT Austin. I'm grateful that you all given me the opportunity to present some of our work on lower bounds for variable length source coding and LQG control with shared randomness. First, I'm going to very quickly show you some notation. Most of it's standard. The main thing is that random variables are in bold and non-random variables are not in bold. I use lowercase for vectors and uppercase for matrices. Unfortunately, this makes it hard to tell what's a scalar and what's a vector. When it's important, I'll let you know. I'm going to use a symbol in the yellow box to denote the set of finite length binary strings. And I'm going to use script L to denote the length of such a string. I'd like to begin by generally motivating communication efficient approaches to feedback control, and in particular, to introduce minimum bitrate LQG control at a high level. It's easier to send fewer bits more reliably and with less physical communication resources. This motivates approaches to feedback control at minimum communication bit rate. If you'll permit me, I'm going to sort of simultaneously try to motivate and formulate this problem. So imagine that we have a remote platform, like the drone in the slide, that's observing a dynamical system, like the vehicle platoon, that it's also controlling. It's going to use the measurements it makes to decide which control commands it should convey back down to the platoon. In this scenario, we're going to assume that the drone has like a very expensive camera, that it can make arbitrarily good measurements of the platoon, essentially for free. But when the drone wants to convey its control commands back down to the platoon, it's got to use a radio. And using that radio is going to incur communication costs. For example, it'll take up a shared channel for some set of time, or it'll expend some of the drone's battery, etc. So I'm going to sort of abstract things to make the communication cost a little bit more concrete. I'm going to assume that the drone encodes its control commands into packets of bits, literally strings of ones and zeros. I'm going to assume that these packets can be transmitted to the control system reliably, which in communication engineering terms means without errors and without delay. Then we're going to quantify communication cost by the time average expected length of these packets. We're going to call this the bit rate. We can now state like a generic goal, which is to minimize this bit rate subject to a constraint and control performance. In particular, in this work, we're going to be specializing this formulation to the LQG control setting and developing lower bounds in the minimum necessary feedback bit rate required to achieve satisfactory LQG control performance. Our general formulation of this problem is going to follow primarily from Silva et al.'s framework for control system design subject to average data rate constraints, which is reference 1. That work considered scalar LQG control with prefix-free binary feedback over a noiseless channel. A lower bound was derived in the minimum required bit rate to attain a given LQG control performance. This bit rate was lower bounded by Massey's directed information. This lower bound motivated the definition of a rate distortion trade-off between directed information and LQG cost. In reference 1, they showed that this trade-off was nearly achievable using dithered quantization coupled with standard Chen-Fanon-Elias style prefix-free codes. We're going to talk more about this in a minute, but dithered quantization generally assumes that the encoder and decoder have access to a shared random dither sequence. Silva et al.'s work was extended to MIMO plants by Tanaka et al. In 3 and 4. Reference 3, they cover rate distortion, where in the MIMO setting, the trade-off is shown to be computable via semi-definite optimization. Reference 4 covers achievability, that's to say, quantizer and source codec designs. Cassina and Hasibi developed an analytical lower bound for the directed information LQG cost trade-off for MIMO plants in reference 5. In that same paper, they demonstrated how these bounds change when the prefix constraints on the feedback code words are relaxed. They also demonstrated that the minimum directed information performance was nearly achievable without dithering. Recently, Durpick and Ostergaard demonstrated that the proof of the directed information lower bound from Silva's original paper doesn't apply when the encoder and the decoder share randomness through a dither sequence. They were able to correct this proof using a new data processing inequality from their paper reference 7. Recently, we also noticed that essentially 2 different notions of prefix-free are used in the papers used to demonstrate achievability with dithering. One notion is used for lower bounds and another for upper bounds. Noticing this and wanting to have a further understanding of how shared randomness affects the lower bounds, specifically in Tanaka et al.'s problem formulation, motivated us to pursue this work that we're going to discuss today. In this work, we're going to first define 2 mathematically consistent extremal notions of prefix-free constraints that can be applied to the feedback channel for LQG control. We show that under either of these prefix constraints, regardless as to whether or not the encoder and the decoder share randomness, the original directed information lower bound still applies. Our proof is going to deviate from that of Durpick and Ostergaard due to us following more from the problem setup of Tanaka et al. We're also going to show what happens when the prefix constraints are completely relaxed. We're now going to formalize the problem mathematically. Here's an overview of the system model. We're going to assume a discrete time Gauss-Markov plant. In general, we're going to let this model be time varying. W is Gaussian process noise, and U is the control input. We're going to measure control performance via the standard LQG, that's Linear-Quadratic-Gaussian cost, which is shown in the corner. We're going to assume full observability. Essentially, the sensor can make arbitrarily good measurements of the plant state. It knows x sub t directly. Then the sensor encoder can use those measurements to produce a code word or a packet via generally randomized causal encoding policy, PE. The code word can be drawn randomly, conditional on the encoder's past observations and transmissions. The code word, a sub t, is going to be a finite length binary string. We're going to let the length of the string vary across time. The code word a sub t is going to be delivered reliably, that is, without errors, without delay, to the decoder controller. We're going to quantify the communication costs as the time average bit rate of the packets we convey from the encoder to the decoder. Since I'm assuming that the channel is error-free, you can think of this cost as the minimum bit rate of reliable communication required to solve the control problem. We're usually going to require the code words to conform to a prefix constraint. These can allow the decoder controller and most generally other people on the network to identify the end of transmission. We'll talk about these in a minute. Given the code word it receives in the history, the controller can randomly draw a control input, U sub t, via its control policy, P sub c, which is then input into the plant. Again, the control input can be drawn based on the controller's past observations and the control inputs it's made. The dither sequence is essentially going to be an exogenous sequence of IID random variables. This sequence sequentially reveals the encoder and the decoder over time. The dither sequence is such that each realization is independent of the past history, which is why we call it shared randomness rather than side information. At each time t, the encoder and the decoder can use the causally revealed samples of the dither as part of their encoding and decoding policies. Dithering is often used in quantization and source coding to whiten quantization noise or to make quantization noise easier to work with. We're not even going to specify the marginal distribution of the dither sequence. In classical dither quantization, they're usually IID random vectors with uniform distributions over the quantizer cells. But we could also have them be, for example, 0 with probability 1 to encapsulate the setting when no dither is available. So now I can summarize our goal in math. We want to minimize the communication cost over legal encoder and decoder policies, subject to a constraint on the LQG control cost being less than some gamma. The specific definitions of the policy spaces we're considering are shown in the middle right side of the screen. The encoder can draw the code word at time t given the plant measurements and dither realizations up to time t, as well as previously transmitted code words. Likewise, the decoder can draw its control input at time t given the received code words and dither realizations up to and including time t, and the past code words its input. So given these policy spaces, the explicit assumptions we've made on how the dither is drawn, and the implicit plant model, we have that the system variables factorize like this. I know these are not very nice to look at, but we're going to analyze the conditional independence relationships between all these things, and any such relationships must follow directly from these factorizations. There's one last part of the problem formulation that we haven't touched on, namely the prefix constraints we mentioned we would apply to the code words a sub t. We're going to consider two of them. The first prefix constraint is sort of the Covert-Thomas notion of prefix-free that's applied to the codebook used at each time t. Namely, any pair of code words that could be sent with non-zero probability at time t cannot be prefixes of one another. We'll call that the strong constraint here. Note that this is the notion of prefix-free that's typically used to establish lower bounds in literature. Note that at any time t, the encoder and the decoder have a lot of common knowledge, like the realization of the dither sequence, but also the past code words that have been transmitted. This leads us to consider a relaxed prefix constraint. We'll call this relaxed constraint the weak constraint. Essentially, it requires that for any given realization of the random variables that are known to the decoder at time t, the set of code words that can be transmitted with non-zero probability, given the realization of that side information, are prefix-free. For example, under this notion, different prefix-free code words could be used for different realizations of the side information known to the decoder at different times. If the code words conform to the strong prefix constraint, any agent who knows the encoding policy at time t can uniquely identify the end of the code word at time t. In contrast, if the code words only satisfy the weak prefix constraint, any agent who knows the encoding policy at time t as well as the realization of all the side information known to the decoder at time t can identify the end of the code word. Put differently, if an agent doesn't know the realization of the side information known to the decoder at time t, it may not be able to identify the end of the code word then. In fact, somewhat confusingly, the weak prefix constraint, rather than the strong constraint, was used to establish some of the upper bounds in the literature that depended on dithering. So regardless as to whether we insist on the strong or weak prefix constraint, we can think of these constraints as being imposed on the encoding policy. You can think of the next three sections as a derivation of our main results. The next thing we're going to do is state a lemma, namely a data processing inequality that's going to follow irrespective of which prefix conditions are imposed. The key lemma that we have is a so-called directed data processing inequality. The inequality is going to follow from this factorization of system variables, as well as the plant model. On the left side of the screen, I have what's called the causally conditioned directed information from the state vector x to the code word a, given the dither and a one-step delayed version of the control input. On the right, I have the directed information from the state vector to the control input. It turns out that under our system model, this inequality holds. We're now going to derive our results for when there's prefix constraints on the code words. Essentially, the main result of this kind of subsection is that regardless as to which of the two prefix constraints we impose, the time average bit rate of the feedback channel must exceed the time average directed information from the state vector to the control input over the same time horizon. I'm going to generally keep the data processing inequality that I just stated at the top of the screen. Remember that the strong prefix constraint says that at every time t, the random variable a sub t is such that its support is a set of prefix-free binary strings. As you might expect, the key inequality we're going to use to show our lower bound is the Kraft inequality. One way of reading the Kraft inequality is as follows. For any random variable whose support is a set of prefix-free binary strings, that random variable's expected length is lower bounded by that random variable's entropy. The next step follows since conditioning reduces entropy. Then we recognize the formula for mutual information in the yellow box and apply the fact that the conditional entropy of a discrete random variable is positive. Finally, you have to note that if you sum this mutual information, you get the directed information on the left-hand side of the DI/DPI. Then you just sum the top line and the bottom line of the inequality, apply the definition of directed information, and the directed information data processing inequality that we stated to get the result. So now let's try to show the bound for the weak prefix constraint. The weak prefix constraint says that if the random variable a sub t is such that for any realizations of previous code words and controls in the dither sequence up to the present time, the discrete finite length binary string in the conditional support of a sub t given this side information is prefix free. This is a bit of a mouthful. So to devise a lower bound, we could just refer back to our distributions over binary strings view of the Kraft inequality, but instead here's another way we can think about it. Let's first fix the time t in the realizations of past code words and controls, as well as a dither. Let's think about inserting a lossless source encoder and decoder in between the sensor encoder and decoder controller. I call these a virtual encoder and decoder in the figure. At time t, the virtual encoder's job is to encode the code word a sub t, which we assume satisfies the weak prefix constraint, into another code word, c sub t, that is also weakly prefixed. Let's assume that the virtual encoder and decoder have access to the past history of controls in transmitted code words, as well as causal access to the dither. Since the virtual encoder is allowed to do nothing and just let c sub t be equal to a sub t, we have this first lower bound. Then we can lower bound the length of c sub t via, if you will, a more traditional interpretation of the Kraft inequality. You can then take expectations over realizations to get the expected length of a weakly prefix a sub t is lower bounded by this entropy, namely the conditional entropy of a sub t given the past code words and controls and the dither sequence up to t. It's probably tough to keep track of everything, but we had this lower bound before. So we can pretty much do exactly what we did for the strong constraint to get the lower bound. This is from the last slide. This slide follows, like before, from subtracting of non-negative discrete conditional entropy and applying the definition of mutual information. Recalling that this is the definition of causally conditioned directed information, we can sum both sides of the inequality to get this. The last step, we use the DI-DPI at the top of the screen. Thus, for the weak prefix constraint, we also have the lower bound in terms of this directed information. Thus, we've essentially proven our main result. Regardless of which prefix constraint you impose, the expected code length is lower bounded by the time average directed information from the state to the control input over the same time horizon. We're now going to talk about what happens when you relax the prefix constraint on the code words. The only difference in terms of our system model is that now at every time t, a sub t is just a finite length binary string. There's no prefix constraints. Note that the empty string, by definition, is a finite length binary string. So actually, the encoder can choose to send nothing at a given sample time. Our DPI still holds, so I'm going to keep it at the top of the screen. Our lower bound follows from this key inequality, which is due to Spinkovsky and Verdue, which says that if a sub t is a random variable whose range is a set of finite length binary strings, then its expected length is lower bounded by this particular function of a sub t's entropy. We don't have a closed form expression for this theta inverse function, but since we know theta is increasing in concave, we can prove that theta inverse is increasing in convex. We're going to need that later. We know from our work on our bound for a strong prefix constraint that the entropy of a sub t satisfies this bound in terms of this particular mutual information. Since theta is increasing, we can then lower bound the coder length by theta inverse of that mutual information. Then we can sum over t and apply Jensen's inequality and get the lower bound on coder length at the bottom of the screen. Essentially, if you relax prefix constraints, instead of getting the lower bound in terms of the time average directed information, you get the lower bound in terms of theta inverse of the time average directed information. So we can actually use these lower bounds to derive rate distortion functions for our originally proposed optimization. The optimization on the left is the one that we proposed, where we minimize code word length over policies with whichever prefix constraints are prescribed. The optimization on the right is over general causal control policies, which are more general. For example, the encoder need not send binary code words to the decoder, but can instead send any continuous valued message. And we're optimizing directed information rather than code word length. Since the directed information lower bounds the code word length, and since this optimization is performed over a more general policy space, we clearly have this lower bound. It turns out that, actually by reference 3, these optimizations are actually tractable and can be computed via semi-definite optimization. They also neatly extend to the infinite horizon case for time invariant plans. Now I'm just going to close with some quick thoughts. One thing to note is that both prefix constraints we considered in this work were time variant. The stronger prefix constraint only requires that the code words potentially transmitted at every time t be prefix-free. However, it says nothing about code words used at different times being prefixes of one another. One could imagine a stronger time invariant prefix constraint where such behavior is precluded. We could insist that no code word that could possibly be used at any time could be a prefix of any distinct code word used at any other time. Since this would be more strict than even our strict constraint, we'd expect that our lower bound would hold under this requirement. However, potentially a tighter lower bound might hold. Notably, our recent work demonstrates that a time invariant prefix code can be used to attain performance close to the minimum bit rate predicted by the lower bounds we discussed in this present work. It's also notable that you can use these bounds that we've discussed here to derive other rate distortion optimizations and solve them in other ways other than semi-definite programming.